What if I told you that science as we know it nearly ground to a halt hundreds of years ago?
Hmm.
That the brilliant minds charting our universe were tangled in
Hmm.
this massive web of numbers, totally unable to see the cosmic truth right there in front of them.
That's a pretty stark picture.
Some might whisper it was, a dark age for discovery, a time when progress was basically held captive by sheer, overwhelming arithmetic.
It certainly felt that way for some.
But then, this unassuming little breakthrough emerged. An invention so quiet, really, yet so profound, it changed absolutely everything. Welcome to the cool, weird, and possible.
And that mathematical innovation, it really did pull science back from the brink. To really get how critical it was, we need to picture the scene. Early 17th century.
Okay.
Imagine Johannes Kepler. He's this determined, really gifted scholar arriving in Prague,
Right.
and his mission to collaborate with Tycho Brahe, the most renowned, the most meticulous astronomer of his time.
Tycho Brahe. I mean, the name alone sounds grand, almost eccentric, doesn't it? The guy with the legendary notes, and wasn't there a story about a gold nose?
He definitely had a prosthetic nose, yes. Silver or brass,
Hmm.
depending on the account. It was quite the character, noble-born, known for a lavish lifestyle.
Right, the observatory castle and everything.
Exactly, Uraniborg. But his scientific contribution, absolutely foundational, Brahe had dedicated an astonishing 2 decades.
2 decades, wow.
Yeah, year after painstaking year, just compiling astronomical data. And it was data with a precision nobody had ever achieved before.
So not just good data, but like revolutionary data.
It was the bedrock, the
Yeah.
absolute bedrock for Kepler to build this completely new understanding of the cosmos.
Okay, so Kepler has this incredible, super precise data. Every scientist's dream, right? But then he hits this wall trying to map Mars' orbit. You said it was painfully slow. Why? What made the math so agonizing?
Well, the computational burden was just immense. Kepler was brilliant, no question, but he was completely shackled by the tools they had back then.
What kind of tools are we talking? Or lack thereof?
Think about trying to solve a giant, really complex jigsaw puzzle,
Okay.
only you're missing half the pieces and there's no picture on the box to guide you. That was their computational world.
Wow.
Scientists were literally doing these enormous calculations by hand. Multiplication, division, square roots, trigonometric functions on huge numbers for years just to pin down one planet's path.
Years. Just for Mars.
It was a grind, a mind-numbing grind that could, frankly, break even the most dedicated person.
That sounds unbelievably frustrating. So these geniuses looking at the stars, they have all this amazing data, but they're basically stuck doing sums by hand forever. Like trying to dig a swimming pool with a teaspoon.
That's a pretty good analogy, actually. It absolutely was like that. Now, Kepler had already managed to figure out 2 crucial things, 2 laws.
Right, he published those earlier.
In 1609, yes. First, that planets move in ellipses, with the sun at one focus, not circles.
Big deal, that one.
Huge. And second, that a line connecting a planet to the sun sweeps out equal areas in equal times. And what's really interesting is he found them in reverse order. He got the equal areas law first, then realized the paths had to be ellipses.
Huh. That is odd. Science doesn't always go step A, step B, does it?
Rarely.
Yeah.
It shows how discovery can twist and turn before the whole picture comes clear.
And these laws, they were a total game changer.
Right.
Because you couldn't even think about them using the old Earth-centered model, the Ptolemaic system.
Exactly. That's a crucial point. The Ptolemaic model, with all its complex circles on circles, epicycles, difference, it basically forced observations into that Earth-centered box.
Right.
Copernicus, proposing a sun-centered model, simplified things massively. Kepler then took Brahe's super precise data, and instead of forcing it into circles, he let the data tell him the shape.
And the data screamed, ellipse.
It screamed ellipse, only ellipses fit. And this willingness to ditch the old model, to trust the math suggested by the observations, that was key.
It really shows how the framework you use shapes what you can even find.
Absolutely. And it connects way back, too. Kepler's first law, the ellipses. That relied partly on ancient Greek studies of conic sections. People like Apollonius of Perga figured out the math of ellipses centuries before anyone thought of applying it to planets.
Wow. Pure math, just waiting for its moment in the universe.
Precisely.
So, okay, he's got these 2 laws. But then, you said he spent over 12 years searching for more patterns, more cosmic harmonies like the Pythagoreans.
Yes, he was deeply influenced by that idea, that the universe should have this underlying mathematical beauty, like music. But despite all his searching, trying different combinations, nothing clicked for that third law. 12 years is a long time to wrestle with data.
So what happened? Why, after all that struggle, does this marvelous insight just suddenly appear in his head in 1618?
Well, Kepler himself described it that way. March 8th, 1618, boom, the idea hits him. His third law,
Which was
that the proportion between the periodic times, how long planets take to orbit, is precisely 1.5 times the proportion of their mean distances from the sun.
Okay, say that again. Proportion. 1.5 times.
Right. Think of it like this. If you take the logarithm of the ratio of the orbital times of any two planets, say T1 over T2, that number equals 1.5 times the logarithm of the ratio of their average distances, R1 over R2.
Logarithm. There's that word again.
Exactly. Logarithms turn multiplication and division into addition and subtraction, and they turn powers and roots into multiplication and division. So that relationship, log, T1, T2, log R1 over 2, is the same as saying the square of the period is proportional to the cube of the distance. T squared proportional to R cubed. That's Kepler's third law as we usually learn it.
Ah, okay. So the familiar version comes from unpacking that logarithmic insight.
Precisely. And get this, he actually made some math errors initially, dismissed the idea.
Oh no, after 12 years.
I know. But then, May 15th, it came into his head again. He rechecked the calculations, and this time they fit so perfectly he thought he must be dreaming.
Wow. But why then? What changed between, say, 1617 and May 1618?
That's the million-do-it question, isn't it? Why did this logarithmic way of seeing the pattern suddenly crystallize?
Okay, I'm sensing a connection here. You keep mentioning logarithms. Is it just a coincidence that a certain book, John Napier's Mirifici Logarithmorum Canonis Descriptio?
The description of the wonderful canon of logarithms.
Right, published in 1614. Is it a coincidence Kepler first saw that book near the end of 1616? This invention, designed just to make sums easier, might have directly led Kepler to a fundamental law of physics.
It seems far more than a coincidence. Kepler was immediately excited about logarithms. You can imagine why, right? Drowning in calculations.
Oh yeah, like finding a calculator after years of using an abacus.
Exactly. He even wrote his own book explaining logarithms in 1621. And crucially, his initial statement of the third law. It was in that 1.5 times the proportion form.
The logarithmic form.
Precisely how it would look if he was plotting his data on what we'd now call log-log graph paper. It really strongly suggests the tool itself enabled the discovery. A tool meant just to save labor revealed a deep truth about the universe.
And yet his own mentor, Michael Meslin, apparently told him off for being interested. Said something like, "It's not seemly for a math professor to be childishly pleased about shortening calculations."
Yes, perhaps jokingly, perhaps not. Academic rivalries and perspectives were different then, but Kepler clearly knew it was more profound.
He must have. He dedicated his ephemerates, his astronomical tables for 1620 to Napier, who had actually died a few years earlier in 1617.
Right, and the cover illustration, it shows Galileo's telescope, symbolic of new observations, and an allegorical figure wearing a wreath made of.
Let me guess, logarithms.
The Naperian logarithm, specifically, his original formulation. Kepler obviously saw the deep connection.
So Napier's big idea was these artificial numbers. How do they actually turn multiplication into addition? Like switching gears.
That's a great analogy. Napier essentially created a system where every number had a corresponding artificial number, its logarithm. If you wanted to multiply two big numbers, you'd look up their logarithms in a table.
Okay.
Add those logarithms together, addition being much easier and faster than multiplication.
Right.
And then look up the number corresponding to that sum. That number would be the answer to your original multiplication problem. It turned a hard operation into an easy one.
Magic. Well, mathematical magic.
It felt like it. It was this huge leap, desperately needed by astronomers, navigators, anyone dealing with complex math.
An amazing story. Science saved by a mathematical shortcut.
Yeah.
But, you know, here on Cool, Weird, Impossible, we love the strange backstories. And the origin of logarithms itself involves some pretty wild tales.
Oh, it definitely does. Before logarithms, there was this older technique called prostaphyresis.
What now?
Prostaphyresis. It's Greek, basically meaning addition and subtraction. Tycho Brahe himself used it. It involved using trigonometric formulas, identities involving sines and cosines, to turn multiplication into addition.
So another way to dodge hard multiplication.
Exactly. But it was, as you said earlier, incredibly fiddly. You needed extensive trig tables, lots of lookups, careful tracking of signs, very nasty calculations, still very time-consuming.
Okay, so where does the weirdness come in?
Well, around 1590, a Dr. John Craig, physician to James VI of Scotland.
Who later became James V of England.
That's the one. Craig visited Tycho Brahe at Uraniborg, his castle-in-the-sky observatory on the island of Fen.
It must have been quite a place.
Apparently so. And Craig saw Tycho and his team using this prostaphoresis technique. He saw how it worked, how laborious it still was.
Okay, still sounds fairly normal for scientist visits.
But now connect that to King James VI's life. He had this dramatic trip to Norway to collect his bride, Anne of Denmark. She'd been delayed, diverted by a terrible storm.
Right, I remember reading about this. The storm was so bad.
So bad that afterwards, back in Scotland, accusations of witchcraft flew. Several women were accused of raising the storm through magic and were put to death. It was a time of intense superstition alongside burgeoning science.
Whoa, okay, that is getting weird. How does this connect back to Napier?
When Dr. Craig returned to Scotland, he told his friend about this prostaphoresis technique he'd seen at Tycho's observatory. And that friend was...
John Napier, Baron of Merchiston.
Exactly. And according to some accounts, it was hearing about this clumsy but necessary computational trick that spurred Napier on. It seems to have motivated him to find a better way, leading him to devote the next quarter-century of his life to developing logarithms.
25 years, wow. All sparked by his friend seeing Tycho's team struggle with trig tables after a royal voyage nearly ended in disaster blamed on witches. It's definitely cool, weird, and possible material.
Isn't it? He even sent some early results to Tycho before publishing. The connections run deep.
And speaking of weird connections, that whole story. Storm-tossed nobles, a mysterious island, a ruler who's part scientist, part, well, almost magician. Does that ring any bells? Like maybe Shakespeare. The Tempest.
It absolutely does ring bells. The Tempest was written around 1610. Now, the standard theory connects it to a real shipwreck in Bermuda.
Right.
But some scholars argue Shakespeare might also have been drawing on the stories filtering back about James VI's voyage, the storms, ending up on this island ruled by the famous astronomer/astrologer Tycho Brahe and his castle in the sky.
Tycho as a model for Prospero. That's wild.
It's speculative, of course, but consider the other links. Shakespeare used the names Rosencrantz and Guildenstern in Hamlet. Those were families on Tycho's coat of arms.
No way.
Way. And Shakespeare was close to the Digges family, English astronomers who knew Tycho. The overlaps between the scientific and literary worlds were surprisingly strong then.
So Tycho, the meticulous astronomer with his island observatory, maybe echoes in Prospero, the magician on his island. That's quite a thought.
It's not completely far-fetched. Prospero's name itself might even hint at it. Providence and sparrow, perhaps a nod to observing the heavens. It shows how ideas were synthesized, just like Kepler synthesized Copernicus, Apollonius, and Napier. These breakthroughs weren't islands, they were intersections.
Okay, my mind is slightly blown by the Shakespeare connection. But let's get back to the math itself. How did Napier's artificial numbers actually work? You mentioned runners.
Right. His original concept was based on motion, purely kinematical. Imagine 2 points moving along lines. One point moves along an infinite line at a constant speed.
Okay, steady runner.
The second point moves along a line segment of a fixed length. It starts at the same speed, but its speed decreases in proportion to the distance it still has left to travel to the finish line.
So it slows down the closer it gets, but never quite stops, like Zeno's paradox.
Exactly like Zeno's paradox. It constantly reduces its speed relative to the remaining distance. Napier defined the distance covered by the first runner, the one at constant speed, as the logarithm of the remaining distance for the second runner.
That's quite abstract, but clever.
Very clever. And this specific way of relating constant motion to proportionally slowing motion inadvertently led him straight to the base of natural logarithms, the number e.
Around 2.718, that fundamental constant just pops out of this thought experiment about runners, even before calculus was invented.
It's amazing, isn't it? Napier's original logarithms were related to 1e, but the core concept was there, emerging purely from this kinematic model of continuous decay.
Building a bridge without knowing the engineering principles, like you said. Incredible.
It really is. Now, his original system was a bit cumbersome. It was another mathematician, Henry Briggs, who collaborated with Napier.
Okay.
Briggs suggested using base 10, our everyday counting system. That made logarithms much more practical and intuitive for everyday calculations. Those are the common logarithms many of us encountered in school.
Right. The ones useful for calculations.
Yeah.
And that partnership made them really take off.
Absolutely. Base 10 logs were easier to work with, and the impact was almost immediate. Just a few years later, in 1622, William Oughtred invented the slide rule.
The slide rule, my grandpa had one of those. Basically a physical calculator based on logarithms, right?
Exactly. Two logarithmic scales sliding against each other. It was the essential computational tool for engineers and scientists for over 300 years, right up until electronic calculators became common in the 1970s.
3 centuries powered by Napier's idea. Amazing. So was Napier completely out of the blue, or were similar ideas floating around? Was it in the air?
That's a great way to think about it. The basic principle that exponents add when you multiply numbers with the same base wasn't totally unknown.
Like powers of 2. 2 squared times 2 cubed is 2 to the 5th. Add the exponents.
Precisely. That concept existed. You can find hints in ancient Babylonian math tablets dealing with powers. And a German mathematician, Michael Stiefel, published tables of powers in the 1540s that were quite suggestive.
So the raw ingredients were there.
The ingredients were there. People knew about powers and exponents. But Napier was the one who systematically turned that idea into a practical, universal tool for computation, driven by that desperate need to ease the burden, especially in astronomy.
So this isn't just some dusty old history lesson then. Logarithms genuinely accelerated science in a way that's hard to overstate, cutting calculation time from years down to days.
It's almost impossible to exaggerate the impact. It enabled astronomers like Kepler and later Newton to make incredibly precise predictions, test their theories against data, refine their models in ways that were simply unthinkable before.
It fueled the scientific revolution.
It was a massive catalyst. It helped shift the whole worldview from just observing and describing qualities to measuring, calculating, predicting, building a mechanical, mathematical understanding of the universe through experiment and computation. Logarithms were like the high-octane fuel for that new scientific engine.
And the legacy is still absolutely everywhere today, isn't it? Not just in history books.
Oh, completely. Logarithms are fundamental in computer science. Think about algorithms for sorting data, searching databases. Their efficiency is often analyzed using logarithms, like logarithmic time complexity. Binary logarithms are crucial there.
Right, how many times you can have something.
Exactly. And in engineering, we use logarithmic scales all the time because they handle huge ranges of values elegantly. Decibels for sound intensity.
The Richter scale for earthquakes.
Exactly. Both logarithmic scales making enormous variations manageable. And in finance, compound interest is exponential, so logarithms are key. In biology, population growth, chemistry, pH values.
Even visualizing data, right? If something grows exponentially, plotting it on a logarithmic scale makes the trend a straight line, easier to see.
Precisely. They're essential for making sense of trends, especially exponential growth or decay. They're woven into the fabric of modern science and technology.
So just like Kepler used this new tool, logarithms, to completely redefine our understanding of the cosmos, today we're using AI, machine learning, massive computing power.
All sorts of new tools, yes.
It makes you wonder, doesn't it? What new cosmic shores, what new fundamental laws, or maybe even insights into ourselves will we discover with these new tools?
That is the question.
And will we, like Kepler maybe had to, need to embrace entirely new ways of thinking, new paradigms, to really unlock the potential of these tools we're building now?
History suggests that's often how the biggest leaps happen. New tools combined with new perspectives.
What an incredible journey. From Tycho's tedious calculations and Napier's runners to Kepler's laws and the foundations of modern computing. A mathematical idea really did save science.
It certainly gave it a massive, much-needed boost.
Well, thank you for joining us on this deep dive into the cool, weird, and possible world of logarithms. It was fascinating.
My pleasure. It's a fantastic story.
If you enjoyed this deep dive, please make sure to subscribe to Cool, Weird, and Possible wherever you get your podcasts so you don't miss our next adventure into the history and future of discovery.